This integral here is called the Gaussian integral. If I tell you solve it using elementary integration methods, you will most likely go mad. We can solve it using Feynman's trick, polar coordinates, or use some clever substitution along with applying Fubini's theorem. In this video, I will show you how to solve this in a clever way without Feynman's trick or polar coordinates. First, we take I equals the original integral. Then we square both sides. And then we change the variable from x to y. If you see the graph of e to the power minus x squared, you can see that it's symmetrical from minus infinity to 0 and from 0 to positive infinity. So you can write the integral like this. Therefore, I squared can be written like this. Now let us introduce a new variable t such that y equals xt. So dy equals x dt. When y equals 0, t equals 0, and as y tends to infinity, t tends to infinity. Now we put in our substitution and then we interchange dt and dx by Fubini's theorem. Now we make a u substitution such that u equals x squared times 1 plus t squared. Then we find value of du and x dx. Now when we plug in our u substitution, we get this value for I squared. Now, e to the power negative infinity converges to 0 and e to the power 0 is simply 0. Hence, the integral becomes dt over 1 plus t squared. This integral's value will be tan inverse of t. Applying limits, we get pi over 2, and on further simplification we get I squared equals pi. So if I squared is pi, then I must be equal to square root over pi. And I is our original integral. Hence, as you can see, we just solved the Gaussian integral in a clever way without polar coordinates or Feynman's trick. Subscribe or sun will come.